Today we're going to be learning how to use pivot table output to compute extra information so that we can create plots for recollection and familiarity data. And more than that, in the advanced section of today's video, we're going to look at how we can plot recollection and familiarity by confidence so that we can see how confidence distributes across different levels for familiarity and recollection-based responses, respectively. It's a bit of an advanced topic, but it's definitely doable. So let's get to it. Welcome to the next video in our PsychoPy tutorial series. Today we're going to be working with the more advanced experiment that we developed last time. In fact, we're going to take some data that I collected off screen from this experiment, and we're going to actually be analyzing it in Excel using pivot tables and some slightly more advanced techniques than we've seen before. So already in my scripting folder, I've got a raw data folder, and I have participated myself in this experiment 5 times over, trying to vary my response strategies up a bit so that my responses aren't all the same. And I have now 5 data files. We can open up any individual one. You'll see here the 6 items that I studied. You'll see here's the test phase that I went through. Here are my confidence responses for each individual item and my selection of whether I said I could re-experience the item, whether the item was familiar, or whether neither were true. And one thing I forgot to do early on, and I just sort of let it go, is I was not going into my stimulus file and randomizing the stimuli for each run. So as we saw in the last video, I could have been randomizing these items so that every time I ran the experiment, it was a different set of items that would be studied and a different set of items that would be new. I forgot to do that. So in every single run of mine, it's the same study items, the same test, but they're in different orders, so it's not a big deal for our purposes. Okay, so step 1 before we start analyzing anything is to merge our data files together. I'm going to use the Python script file here, data merge. And as I showed you in an earlier video, you place your raw data in this raw data folder, then you open the script, you hit execute, and the result will be a merged data file. So we can go ahead and open this file, and this is going to be all the data from the 5 different runs all merged together. And we can see here, if we maximize it, that we have participant number 1. We scroll down, there's 2, there's 3, there's 4, and there's 5. So this is 5 mock subjects worth of data. Now, to remind you in this experiment, every time I saw a test item, rather than rating it as yes, it was studied, or no, it wasn't, I made a decision from 1 to 6, with 1 being I'm sure it's new, 6 being I'm sure that it was studied, and every number in between representing a varying degree of confidence in one direction or the other. So if we wanted, we could revert back to our earlier techniques of analyzing this data, and we could write some if statements to determine whether this is a hit or a false alarm. We could consider a 4, 5, or 6 to be a hit, and a 1, 2, or 3 to be a false alarm. So the way we would do this is we would write an if statement that checks if R10 is greater than or equal to 4, and if it is, assign a value of 1, if not, assign a value of 0, and this is essentially our p_yes column. And as we saw in the previous video, you can copy this down. You have to add a further check to make sure that when you copy this down, it won't fill up the study phase and other areas with stuff. If you're curious how to do that, check out my earlier video. I'm just going to skip past that at the moment. Here, by the way, I'm using a slightly different if statement than you've seen before. I'm using a function called isNumber, and I'm checking to see if R10 is a number, and if it is, then I convert it to a 1 or a 0 for my p_yes column. And so as you can see, this technique, because there's always a number here during the test responses, helps me ensure that I'm not producing 1s and 0s in p_yes in areas where I don't need a 1 or a 0. So again, when I originally showed you how to calculate PS, I said there's a variety of if statements you could use to sort of set it up so you don't calculate 1s and 0s when you don't need to. This is just another way of doing it. So with our data in this form, we can go over and insert a pivot table, much like we did the first time around. We can select all our columns, click OK. With the pivot table, remember, participant always goes in rows. So we have our 5 different participants. In this case, we're going to plot p underscore yes just to be consistent with what we've seen before. And let's just look at the difference between old and new items. And remember to change p underscore yes from a count to an average. Oh, and by the way, I've got an error here. This is actually a good learning opportunity. Why am I getting all these errors? The reason is that if you look at my if statement, I've actually surrounded 1 and 0 with quotes. So they're not being entered as numbers, they're being entered as the letter 1 and the letter 0, if that makes sense. If I take the quotes away, this is going to solve the problem. So I'm just going to do that, copy it down for the entire column, and if I update my pivot table, everything should now work. Yes, there we go. So this is showing us the probability of saying yes, basically. Picking a 4, 5, or 6 to an old item, which is 83% across all my participants, and yes to a new item is about 10% across all my participants. So that's pretty good. Now, we have more information than we had before, so let's utilize some of this. One thing we can be interested in is what is the probability of a recollection response to an old item or new item, a familiarity response to an old item or new item, or a neither response to an old or new item. The way we can do this, imagine what we want out of our table. So the best way to think about how to build your table is to kind of visualize what you might want out of a figure. So imagine that we have old items here and new items here. So we have 3 bars here and 3 bars here. For old items, we want to know how many R responses were there, how many F responses were there, and how many N responses were there. And for new items, we want to know something similar. So in order to do that, we need to, in columns, have both new and old, but then below that, we need to separate R, F, and N. R, F, and N. So we need to find the R, F, and N variable, which if we look in our data file over here, it's this column, and that's key test rfn.keys. So key test rfn.keys, we're going to drag that below old and new because we want old and new to be sort of the top level, and then within that we want to see responses to these different item types. Okay, so I'm going to center things just to make it a little easier to see, and I'm going to change the size of some of these columns. So sometimes the pivot tables automatically make things a little difficult or a little challenging to see. But here we go. So for new items, there were some F and some N responses. There were no R responses. That's why R is not showing up here. For old items, there were F, N, and R responses. But the data at the moment is not very useful. It's basically telling us the average accuracy of items. So when an item was old, to call it R is correct. If it's old, to call it F is correct. I'm not sure why it's counting that there. This is basically an odd way to organize your data. So what we want to see instead for this kind of data is we actually want to see counts. And so bear with me for a moment. This will probably become clear as we start to work with this a little bit. So this data is a little better because now we can actually look at it and see, okay, for subject 2, 3, 4, and 5, there was one new item that they gave an F response to, and the rest they gave N responses to, which is good, meaning they don't remember them. For studied items, we can see that some subjects recollected 2 studied items, other subjects recollected 4 studied items, and then we can see a distribution of F responses here. So if we wanted to, we could calculate our own averages to figure out how many R responses people gave to old items on average, how many F responses, and how many N responses. And we can then look at, on average, how many N responses are people giving to new items, how many F responses are people giving, and so on. Now this is an okay starting point, but in reality, we don't want to deal with counts. The same way that when we were dealing with p underscore yes, when we were looking at our pivot table originally, we weren't super interested in p underscore yes. Rather than knowing the raw number of items that people were giving recollected or familiar responses to, we want the proportion of items that people were giving recollected or familiar responses to. So you should get used to dealing with your data in proportions. So we're actually going to get rid of this. And what we're going to do is create our own table that contains the information we need, and we're going to use the information out of the pivot table to construct it. So let's create a table over here. And to make things a little easier on myself, these extra columns that I don't need to see right now, I'm going to highlight them, I'm going to right click, and I'm going to click on hide, because I just don't really need to see them, and they're getting in the way, and they're eating up a lot of screen. Okay, so here's the original table. I need to convert all these numbers into proportions. So here's what I'm going to do. I'm going to have a new table that has a column called subject, and the value here is going to be A4, this cell. Make sure, by the way, that you type in equals before you try and click on the cell A4, or you can type equals and then you can type A4, but for this entire table that we're making, we're going to heavily be using the equals sign. So whenever you want to type in an equation or anything, you always start with equals. Hopefully you guys have picked that up by now, but in case you haven't, you are going to see me using equals a lot. So I type in equals, and then I can either click on a cell or type in its name. And if I copy this down, then I end up with a column that identifies my different subjects. Great. So now for new items, I want to know how many R responses were there, what proportion were there, how many F and how many N. And for old items, I also want to know the proportion of R, F, and N. And I'm going to get a little fancy here, and I'm actually going to merge these cells together, and I'm going to merge these cells together, and I'm going to center things. And I'm doing this all to help keep myself organized so I can clearly see what's going on in my table. Okay, for new items, we know that this is always 0. We know that there were no R responses. If there had been at least one, then we could calculate something, but we know that there's none, so we're just going to copy this down and have this be 0. Now, for the proportion of F responses, we are going to calculate this. So type in equals, and then type in this case, B4. And you'll notice that we're now selecting this cell B4. By the way, pivot tables are a little funky. If you try and click on them, sometimes instead of selecting the cell, it will give you this big complicated mess. You don't want that. Just type in B4 to get the cell. And we're going to divide by D4. So notice what we're doing here. We're taking the number of familiarity responses to new items, and we're dividing by the total number of new items, which is shown right here. And we can just hit enter. We can copy this down, and we can center it if we like. And we have now just calculated the proportion of an F response to a new item. We're going to do the same thing over here. Again, if I try and select the cell, I get this big ugly mess. So it reminds me that I should go C4 divided by D4. Press enter, and I will copy this down. And we can see the proportion of new items that received an N response, which is essentially a correct response. I can do the same over here, though I actually need to unhide some of these columns because I hid the total for old. Although now that I'm looking at it, the pivot table is doing something a little funky. It's, for some reason, thinks that there were 12 old items, but that's not true. There were definitely 6. I guess it's counting up 6 blank cells somehow. So we're going to do this, and we're going to divide. We'll just manually divide by 6, because we know it should be 6. There were 6 studied items. So, E4, oops, actually, I've made my first mistake here. I want to calculate the proportion of old items that had re-experience responses, and I've just selected the F column. So I need to move this over here. So it should be G4 divided by 6. I'm going to do the F response right now. That is E4 divided by 6. And I'll do the N response, which is F4 divided by 6. I'm going to copy all 3 of these, and I will highlight these cells like this and click paste, and it will fill everything in for me. And I can center everything. Once again, these are numbers, so I'm going to go ahead and format the cells to be numbered so that things are a little easier to read. And it's a little easier to read, but it's still fairly messy, which is why we need our summaries. So let's construct a really quick figure. So we need means and standard errors. To calculate means, we use an average. You can check out my previous videos if this looks foreign to you. For standard error, it's standard deviation divided by the square root of the count of the number of scores that went into that standard deviation. And we can just copy this over, we can center it, and we can go ahead and format the cells. Now, we know for new items and old items, the proportion of times on average that people said R, that people said F, or that people said N. So we could go ahead and plot this into a chart. And so this is probably largely review, although I hope it is, at least I hope it is anyway. So let's go ahead and let's plot old items first. So first we're going to plot the probability of an R response. And for old items first, we'll click on the old item mean, hold control, click on the new item mean. Then we'll display the probability of an F response. We'll click on the old mean, then on the new mean. We could plot out the probability of a new response, but it's actually usually not really done, because if you look at the numbers for any individual subject, if you add up how many R's and how many F's, then the proportion of N responses is always whatever is left over. So these three numbers always have to add up to 1. 0.17 plus 0.83 is 1. 0.17 plus 0.83 is 1. 0.33 plus 0.5 plus 0.17 is 1. So if you know R and you know F, you always know N, and as a result, if you notice in papers and stuff, people will almost never plot the proportion of N responses because it's kind of redundant. So we'll just leave it at that. We'll go ahead and go back in, however, and select proper labels for our categories. So we want old, comma, new, and I'm holding control to select those two cells there. We need to make sure that we add a legend. We need to make sure that we add axes labels. And we need to go in and make sure that we add standard error bars. So remember to go into Custom, Specify Value. And the same way you selected the means is how you select the standard errors in the exact same order. And there we have it. So the probability for an old item of responding R is a little under 50%, but it's very close and not statistically different, most likely, from the probability of saying F to an old item. And then the probability of an R to a new item is 0. That's why you don't see a bar. And the probability of S. So these are false alarms, and these are hit rates. Now from this stage, there's a few more advanced things that you could do. One thing that you could calculate is something known as the independent remember no procedure. And that is basically an adjustment to how you calculate your F responses. So think about it like this. Think about what happens in our experiment. When somebody is looking at a test item, trying to decide if they can recollect it or not. If they can recollect it, they're going to give you an R response. If they can't recollect it, they'll give you an F response. But when they give you an R response, it doesn't mean that the item isn't familiar. It just means that the item is recollected. So essentially, when people give a lot of R responses, the proportion of F responses must go down, even if every R response they provide is also familiar. This is a bit of a problem, because it means that, look at subjects 4 and 5. 67% of old items were responded to with an R, and only 17% of old items were responded to with an F. Does this mean that these subjects experienced less familiarity for all old items? Well, probably not. Probably some of these items they could recollect were also familiar, and if we'd given them the option, maybe they could have also said that they were familiar. So one way to adjust this is to calculate independent familiarity. We'll just call it IF here. And let's calculate it separately for old and new items. So the way you calculate independent familiarity is you take familiarity and you divide it by 1 minus recollection. And so we can just copy that down, and we can do it over here as well. So familiarity divided by 1 minus recollection. We can copy this down. So what is this formula doing? It's basically adjusting the familiarity responses based on the opportunities to provide them. So look here, this subject, their independent familiarity rating was 100%. That means that whenever they didn't make a recollection response, 100% of the time they made a familiar response, meaning every time they could have made a familiar response, they made a familiar response. For these subjects down here, remember how low their familiarity responses were. 0.17 is very low. But if you consider that they couldn't make that response when they made a recollection response, then really half the time when they didn't make a recollection response, they made a familiar response. So a better representation of their overall familiarity for old items is 50% rather than 0.17. If this concept still feels a little hazy to you, it's okay. You can ask about it in the lab. But for our purposes, we're just going to accept that this is an adjustment that you can do to come up with alternative values for familiarity. And what we're going to do is we're going to update our figure over here and replace the familiarity values with our independent familiarity values. So let's right click here and go to select data. We're going to adjust the probability of familiarity. And rather than taking these two values that we have here, we're going to replace them with the independent familiarity values. So we'll click here and we'll hold control and we'll click here. Now we also need to adjust our standard error bars. So we can right click and click on format error bars. We can go down, click on specify value, and we can replace the values that are there with the values that have been recently calculated with our independent familiarity correction. And there you have it. And so this gives a slightly different estimate of the level of familiarity. And now you can see that by this second estimate, we're guessing that familiarity for old items is actually higher on average than recollection for old items. Now the choice about which correction to do on the data will come from theoretical considerations. So just looking at the data won't really tell you, but I wanted to show you guys how to do this because this is a correction that we make occasionally in my lab, and it's important that you guys understand how to go from the raw data following all these steps and get to this point. Let's leave everything here and create a new sheet. And let's create another pivot table and do just a few more remaining things with our data. So we'll go over here and we'll select all the columns that make up our experiment once again. Of course, we could throw word color in the columns. We were just using old new status over here on this sheet, but we could have done word color if we wanted instead. If we were interested in maybe the blue items and the green items would behave differently, that's fine too. You can mess around with different column setups. We'll just stick with old new because it's simpler for our purposes at the moment. We'll throw participant into the rows. And of course, if you were so inclined, you could learn about the average accuracy of different conditions. So by throwing in test keys, conf keys, and getting an average, you're getting the average confidence response. So on average, if you average together all of these numbers for old and new items separately, what's the average confidence response? You can see that studied items are on average getting about a 5. New items are getting about a 1 point, well, here are the averages, 1.4 and 4.9. Now we don't actually usually analyze the data in that way, but if you wanted to see if we could, you of course can. And of course we can throw reaction times and so on in here if we're interested in reaction times. The one other analysis I wanted to show you, however, dealt with breaking up recollection and familiarity responses based on level of confidence. So sometimes we're interested in issues such as how confident were the different responses, such as recollection and familiar. You could, of course, throw that variable, the RFN variable, into columns. And of course, if we sort this and we separate out our columns a little bit so we can actually see what's going on here, you can see the average confidence rating of the different categories. You can see R's. In this case, I gave an R a 6 every time I had a recollection. This is fairly common, although, 5 or 6 is more common to see, so some variation is normal, but typically recollections are very highly confident. You can see that familiarity responses, on average, were less confident than the recollection responses. They're still fairly confident because I was remembering them, but sometimes I just couldn't actually recollect the item, and so I provided a familiarity response. You can see that the N responses I provided were often very low confidence. And you can see that when I was false alarming, when I did think a new item had been seen, I gave it an F response. I was giving it an average response here of 2, here of 4, here of 4, here of 4. So you can look at the average level of confidence of the different items this way. Another way that we look at this, however, is sometimes by putting confidence in the columns. And let's bring in PS one more time, and we're just going to leave it as a count. That's fine. And we're going to get a big table here. So this is going to be the biggest data table that we're going to look at together. And it's going to seem like a lot at first, but we're going to break this down. So first of all, here are all the new items, and here are all the old items. And in fact, as before, there's a bunch of other columns that we don't need to see, so we're just going to hide those. What this table is plotting out is it's saying for new items that were given an F, how many of them were also given a confidence rating of 2, how many were given a confidence rating of 4. For new items that were rated N, how many of them were given a rating of 1, and you can see that many of them were, how many were given a rating of 2. For new items, it's kind of bare. Let's look at old items here. For old items that were rated F, how many were given a rating of 3? Only 1 across all the subjects. A rating of 4, 2 across all the subjects. A rating of 5, 6 across all the subjects. And a rating of 6, 3 across all the subjects. You can see that for familiarity-based responses, the most common rating to provide is a 5. It kind of peaks around 5 and then it subsides. You can see that for old items that were rated R, they were essentially all given 6s. So why am I presenting data this way? Well, we sometimes plot out the distributions of old and new items that were given an R or an F response based on their confidence level. In order to do this, we create basically a very similar table as what we saw before. So we're going to start with our subject numbers. It's always good to have subject numbers in your data so you can identify who you're looking at. Again, not identify them by name or anything, but just make sure you know this is subject 5 and I'm looking at them from table to table. I can see how their data lines up. Then we're going to have new items that were given either R or an F response. We're going to ignore the N responses. And we're going to look at confidence values 1, 2, 3, 4, 5, and 6. So this is going to be a fairly big table. We already know that the R responses are going to be essentially absent for this data set, but once in a while when you're actually conducting experiments, you will find that people make R responses to new items. It's rare, but it happens. Going to merge these together. Going to merge these together. Going to merge this together. So this is, again, the biggest table that we're going to be constructing together. And I'm just going to copy this. I'm going to paste it over here. And I'm going to relabel this old. Now, we don't have many subjects, and they didn't have many trials, so a lot of these cells are going to be blank, but I want to show you the theory of how you would actually construct this table. So let's start with the F responses here. For F responses that were given a confidence level of 1, we can look back over here and see that there actually were none, so it's just going to be 0 every single time. So we're going to go ahead and insert a 0 there. For F responses that were given a 2, we can calculate that by taking B5 and dividing it by H5. So let's do that. B5 divided by H5. There were no 3s. 4s were C5. So new items that were rated F and given a confidence rating of 4, they're in this column here. So we're going to take C5 divided by H5. So C5 divided by H5. The rest are all zeros, and these are all zeros. I could have left out this whole R section, but again, just so you can see how it's done, I'm leaving it in. So we're going to copy this. I'm going to highlight these cells and paste, and we can now start to see our table getting filled out. It's not too exciting for the new items because it was most of the new items, the responses were ends, and we're not plotting the ends, but things will become more interesting for the old items. So for old items, we know that these are all zeros because if you look back over here, old items that were given a rating of R we're only ever given a confidence rating of 6. So Q5 is the cell we're going to look for, and we're going to divide by 6 because the pivot table is counting things up a little weird. So we go Q5 divided by 6, copy this, paste down. We can center if we like. And finally, and these cells will have the most stuff filled out compared to the rest of the table. I'm pretty sure the F responses, yeah, they start at 3. And that is I5. So 1 and 2 are 0. 3 is I5 divided by 6. Let's just double check that. So old items that were given a familiarity response and rated a 3, that's I5 here. So J5, K5, and L5 are going to fill out the rest. So let's just do this real quick. J5 divided by 6, that's the 4s. K5 is going to be the 5s. And L5 is going to be the 6s. And we'll copy this, and we'll paste it. Okay, we're doing a lot of work here for a fairly barren data set, but again, bear with me for a moment. Last thing we need are averages, so means and standard errors. We're actually not going to calculate the standard errors this time around because adding them to the figure is rather tedious work, and for just this simple example, there's really no point. I'm pasting things one at a time. I could be highlighting this whole area and pasting it in, but I just wanted to sort of show it to you coming together. One last thing. Let's go ahead, and I'm just going to format these as a number, as I typically do. Okay, so we have a whole bunch of numbers here. More numbers than you probably ever thought you wanted to see in a recognition memory experiment. What do we do with them? Because honestly, frankly, there's too many numbers here to try to eyeball this to figure out what's going on. So this is where you need a chart. So if you haven't been keeping up with your chart skills, you really need to go back and watch some of those earlier videos so that you know how to make charts. We're going to go in here and go to select data. And what we're going to do is we're going to plot for old items the probability of R based on the 6 different confidence levels. And what we're going to do is actually just click and hold and drag across so we get all 6 of these means. And we'll just hit OK. And then we're going to add in for old the probability of familiar response across the 6 different confidence levels. So we're going to click here. We're just going to hold, and then we'll click OK. And we'll click OK. And what you can see, so we should go ahead and label this even further. So actually, let me do that. Let me practice what I preach here. And we will add some axes titles, probability. This is confidence level. And again, we should add error bars. It's just rather tedious to do it. And were this a real data set, I definitely would. But for our purposes, what we've plotted here are the distributions of R responses based on confidence and of F responses based on confidence. So what you can see is that when people made an R response, they were always 6s. There's no, in fact, 5, 4s, 3s, 2s, or 1s. In a real data set, you probably see a few 5s, but that's about it. So you can imagine this is a highly skewed distribution that peaks here, rapidly declines, and then it levels off like this. Now for F responses, they behave quite a bit differently. They are more spread out. You can see they peak at 5. So most F responses that people give on average have a confidence level of 5. Some have a confidence level of 6. Some have 4. Some have 3. And if we had more subjects and more items, we would see this distribute all the way down to the bottom. And so we could go ahead and construct a version of this graph for the new items. I'm actually going to skip that because it's essentially going to be an empty graph. It's not really going to be all that interesting. You, of course, could do it with your version of this data set if you'd like. But this is one of the more advanced things that we ever look at as a group. And it's important to know how to go from our original data set and first sort based on old and new and recollection and familiar and produce a figure like this, including the raw R and F scores, and the R scores combined with the independent F scores. And it's also important to know how to create distributions like this. So it can be a little complicated. You might have to go over this video one more time before it fully sinks in, but definitely make sure you understand this stuff. It will be very helpful to you to be able to think in more sophisticated ways about your data and to be able to plot things in a more complex way like this. One last minor thing that I'll bring up before we go is I've been using p_yes for all these tables, but in reality I could have been using any variable from the test because we're just counting up the number of times that the p_yes variable existed when an item was rated 2 in N, or 6 in R, or 4 in F. So if you're not sure what I mean, give it a try. In fact, I'll do it with you right here. I'm going to take p_yes out, and I'm going to throw in one of the reaction times. I'm going to leave it as counting, and look, our table doesn't change. None of our values change. Everything's the exact same. Of course, if I take this out and leave it out, you'll notice that our figure goes away. So when we are creating these kinds of data summaries with R and F values, we actually could kind of use any variable from the test we want. Because remember, we're just counting up the number of times an F or an N response occurs, and we were just using PS to say, okay, when you find an item that's 6 in R, count that this exists. So we could have counted that this exists, or that this exists, or that this exists. It doesn't really matter. It's a trivial point. If that's starting to confuse you, then just do what I did in this video whenever you're creating your data files. Don't worry too much about it. But it's just something I wanted to point out for the more advanced users. Anyway, that wraps us up for today. In our next video, we'll probably look at using images instead of words in an experiment, and we may look at getting ratings at the study phase, which you can use to conditionally sort items in your data file. So some even more advanced stuff that you can do with your data. So hopefully I haven't scared anyone off, and if I haven't, then I'll see you next time.